Hiro for inviting me to this nice meeting, and I'm very happy and enjoyed this stay in this beautiful city. Okay, today I would like to talk about my recent work for constructing the heterotic string field theory. This is the collaboration with the Tatsuya Sugimoto. He's not the well-known Sugimoto-san, but he's one of the PhD students in the Yukawa Institute. Okay. Let me start with some brief introduction, but I think that for the audience in this conference, I just simply pointed out that I mentioned that the superstring field theory is one of the approaches to maybe the most conservative approaches to define the superstring theory non-perturbatively. But for such a superstring field theory, we need a complete superstring field theory, including both the Nebu-Schwarz sector representing the space-time bosons and also the Ramon sector representing the space-time fermions. Okay, but such a complete theory is not constructed long time, and that is a long-standing problem. But the recent progress, recently we have big progress, in particular for open superstring field theories. And mainly that there are three complementary approaches called that first that Wess-Zumino-Witten-like approach, which is proposed first by Nathan Berkowitz for the Nebu-Schwarz sector, and we, Okawa-san and myself, extended to including the Ramon sector. And the second one is, I call it as a homotopy algebraic approach that based on that A-infinity structure in the open string case. That is first proposed by the Munich group, Konopka and Zaks in 2014, and then completed including the Ramon sector by Okawa Takezaki 2 years later. And the third one is that Ashok's proposal, based on the Ashok's proposal, his theory is mainly for the closed superstring, but extended to the open string case by Munich group, Konopka and Zaks, that soon. Yeah. But for closed superstring case, for closed superstring, there is only the complete theory by Ashok's approach, sense approach. And no complete theory based on the remaining two approaches, so we should construct them, I think. So today we would like to first consider the heterotic string field theory, the simpler one. Okay. The first I considered it that based on the homotopy algebraic formulation. In the homotopy algebraic formulation, the superstring fields has two components: Nebu-Schwarz string field and Ramon string. That is in the so-called small Hilbert space in the Gauss number 2 and the picture number -1 in the Nebu-Schwarz sector, and the Gauss number 2 and the picture number -1/2 in the Ramon sector. And since the heterotic string is the closed string, the string field is restricted by so-called closed string constraint, annihilated by B0 minus and L0 minus. And we also impose that another constraint, this one, xy, projection xy on the Ramon string, Ramon component. Here the x and y is defined by this equation, which the x is a so-called picture changing operator, which satisfies this condition. The y is its inverse in the sense that these two satisfy this condition. And if we impose this constraint, the Gauss zero mode dependence of the Ramon component is restricted in this form. And we denote this restricted Hilbert space is H-less. And here I should note that this phi r, small phi r and psi r, the two components of the Ramon string field, is just it is quite natural in the approaches of in the BB formalism approaches. I mean that is just corresponding to the field and anti-field respectively in the so-called gauge fixed basis. And we also introduced for constructing the string theory action, string field theory action, that the symplectic form that is defined from the just a conventional BPZ inner product by this form. Since I import that this constraint in this restricted Hilbert space, symplectic form of this restricted Hilbert space is defined by this form, inserting the inverse picture designating operator for the Ramon sector. And we also introduced the string products. That is that I denote that L sub n. That is a string, some graded symmetric product mapped from the three n string fields to one string. And we also call that the simple BRS charge is including this product, that one string product called. And then if this string products is cyclic L infinity algebra, which means that they satisfy this L infinity relation, and cyclic mean that that is cyclic with respect to this large omega symplectic form, then we can construct the action in this form and prove that and show that and we can show that this action is invariant under this gauge transformation. So yes, picture number. Picture number is that some quantum number in the language of the first quantized Hilbert, first quantized superstring. Covariant? Nebuchadnezzar's component has integer picture number, and the Ramon component has a half integer component. But I also restricted that the Nebuchadnezzar's component is just a -1 picture number, a -1/2 picture number. Okay, so if this string product satisfies these conditions, we can construct the action and gauge transformation. So the problem is reduced to how to construct this string product with proper ghost and picture number. I forget to mention that this adding furthermore this condition plus, but this string product have some proper ghost number and picture numbers. Proper mean that I explain shortly. So if we construct this L infinity structure string product satisfying the L infinity structure with proper ghost and picture number, then we can construct the string field theory. So the problem is how to construct it. Yeah, but we know the assumption is that we know that the bosonic product. Bosonic means that heterotic string without any picture number. Heterotic string product without picture number 0. That is can be easily constructed in a similar way into the bosonic string, and which is this. We know that can be satisfying the L infinity algebra with proper ghost number, but no picture number here. So the construction of this desired L infinity structure or string products by suitably putting that picture changing operator or G0 mode into this mosonic string product. Such a construction for the N-Schwarz sector is first given by the Munich group, and we modify their method to their construction and extend it to the one for both Schwarz and Ramon sectors. Sorry? Ln, yes.
Do they have the same picture number?
All the ln? No. Change, yes. Yeah, I'll explain shortly, soon. Yeah, so what is a proper picture number? First, the string field, Schwarz component of the string field has picture number -1, and the Ramon component has picture number -1/2. So for closeness of this string product, picture number of this n+2 is determined so that picture number is closed in this Hilbert space. So the product, that means that the product of the string Schwarz component of the product must have picture number -1, and Ramon component of the product must have picture number -1/2. So let us counting that. For counting that we consider the case by case. That means to characterize that case, that you consider this product. That means that with this subscript 2R is defined by some Ramon inputs. It's called the Ramon number. That is defined by the number of Ramon inputs minus number of Ramon output. So we have two cases. The output is Schwarz or output is Ramon. Yeah, so if 2R of the n+2 inputs are Ramon state, then the output is Schwarz state. For satisfying this equation, this condition, we have this P must satisfy this condition. And the second case is the output is Ramon state. That should be that the input of the Ramon field must be odd, and then the output is Ramon state, and the P should satisfy this condition. These two equations can be solved by in this way, P equals n minus r plus 1. So the picture number of the product is depend on the number of input and the number of the Ramon input. Okay, but we by solving P solving what the other variable, we solve this to the n equal to P plus R plus 1. We usually denote this one. This is a string product with proper picture number. Okay. Next, this product must satisfy the cyclicity property. But the Ramon number is not suitable to consider cyclicity. So instead, we consider the so-called cyclic Ramon number. Cyclic Ramon number is defined by Ramon input plus Ramon output. The similarity sign is different. And we denote it as a superscript. Yeah. Why this is not suitable for cyclicity? The reason is what? This. The cyclicity means that this Schwarz output, the inner symplectic form of Schwarz component and the Schwarz component of this product must be proportional to with some proper signature to the cyclically move to this Ramon component to the outside, the Ramon component must be proportional to the Ramon component, and the Ramon component of this product must be proportional. But these two must be, and this, okay, this is the, since this, the output is Bushword, that the Ramon number is, Ramon number and cyclic Ramon number is equal in this case. But if you move to this Ramon input to outside, then the Ramon input is decreased by 1, and the Ramon output is decreased by, Ramon inputs decreased by 1, and the Ramon outputs increased by 1. So the cyclic Ramon number is invariant. But if the Ramon number is defined by this minus, then minus sign of the, so that is decreased to -2. So this and this is a different product with different Ramon number. So that is not suitable for considered cyclicity. So first we consider the product with this type of product has definite cyclic Ramon number. In this case, the output is the corresponding two cases. One prime is output is a Bushword's case. This is that just satisfy the same equation, but the output is the Ramon case. The total number of the picture is just -1, 3/2. So 1 less than the proper Gauss number. We call it that picture number deficit is equal to 1. So this product has not does not have a proper picture number, so we cannot use it by in the desired string product which we want. But such a combination often appears as a difference of Q and eta, or nonlinear extension of Q and eta. For example, that first order equation of motion, which is first considered by Berkowitz for open superstring, and I extend it to the heterotic case, and the general form of the proposed by Michael Kreuter that presented it. Yes. So we go on further. It is useful to introduce the so-called co-algebraic representation. So I should explain it briefly. Yeah, first we define the symmetric tensor product of the string field, product space of the string field. That is, we denoted this wedge product that is defined by the symmetrized tensor product of this. And symmetrized tensor algebra is the formal sum of such a the number of the string fields. Then we define the linear map from the n-string symmetrized tensor product to the string product with respect to by using the string product. That we denote that we use the same notation, but this is the string product and this is a linear map. Yeah, and then we can define the co-derivation. It's a map from this symmetrized tensor algebra to the symmetrized tensor algebra, which is defined by this definition. If Ln act on the smaller number of the tensor product space, then that it is defined by equal to 0. If m and n is equal, that is just a linear map, this linear map. And if m is greater than, sorry, this is the inverse. If m is greater than L, then the remaining part is defined by this identity. Then we can consider the co-derivation, that is the formal sum of all the string products. Then the L infinity relation satisfied by this string products is just represented as a nilpotency of the degree of co-derivation L. This commutator is that define the graded commutator by the degree. Okay, then we consider the nonlinear extension of Q and eta. We denoted D and C. D is the name defined by R. That means that this is a dynamical constraint, dynamical L infinity algebra, and that this is a constraint L infinity algebra, which is satisfied. Which is that the two L infinity algebra mutually commutative L infinity algebra, and when here that this pi 1 0 is the projection to the Nebuchadnezzar component. 0 is the Nebuchadnezzar component. 1 is the Ramon component. The 1 is 0 and 1 mean that the number of the Ramon component. The difference of these two L infinity algebra here. If you consider the difference of this L infinity algebra, then the projection is can be removed, and the B is just we considered just before. Then this difference is also satisfied the L infinity algebra, and B could be cyclic. Okay, well, I mentioned that all of these D, C, and D minus C's are not closed in small Hilbert space, because that if that is closed in small Hilbert space, that should be commute with the just eta. But this is just a more non-trivial relation. That means that this L infinity algebra is not closed in the small Hilbert space. Okay, then so we first construct that the cyclic D minus C L infinity algebra. Then it transforms to the then transform this two L infinity algebra D and C to the desired L infinity algebra and simple eta. That is the simplest L infinity algebra, just composed of the one string product. Then if we construct such a similarity transformation, such a similarity transformation, it can be constructed in this way. If we define this f hat is that co-homomorphism, then the similarity transformation by this is just realize this this map, and that this map, and that at that time that the L is represented by this form. Q is a velocity charge, and B, small b is just B times f hat. Now, the similarity transformation preserves that commutation relation properties of this commutation relation property. These L and eta satisfy this condition. The L is just so L infinity algebra, and eta is anti-commute, and L and eta is also anti-commute. So that means that this L is closed in the small Hilbert space. So we can show that if B, and in addition, we can also show that if this big B is cyclic with respect to the simple symplectic form in the large Hilbert space, then that small b is cyclic with respect to the small omega, simple symplectic form of the small Hilbert space, which implies that from this form, this implies that the big L is cyclic with respect to the big omega, because that since this here Ramon component of this product is multiplied by picture changing operator, the inner product of this form reduced to the inner product of this using the simple symplectic form. Okay. Then so if we construct this big B, then the desired string product is constructed. So the problem is not also again reduced to how to construct this such a big B. The big B is characterized, as I mentioned, that the big B is characterized by have a definite cyclic Ramon number. But the disadvantage of the cyclic Ramon number is that cyclic Ramon number has a disadvantage as explained here. I mean that the Ramon number is additive in commutator, but the cyclic Ramon number is not. That means that if we have two co-derivations with a definite Ramon number, 2r and 2s, the commutator has a definite Ramon number, 2r plus 2s. But the commutator of the two definite cyclic Ramon number, 2r and 2s, does not have a definite cyclic Ramon number, but has two components, the cyclic number 2r plus 2s component and the cyclic number 2r plus 2s minus 2 component. So we define the two operations. We call it that commutator 1 and commutator 2, which is defined by the projection onto this each term. The commutator 1 is defined by this component. Commutator 2 is defined as the second component. Yeah, more generally, if L is sum of some such a definite such a co-derivation with definite cyclic Ramon number, L and L prime, then we define it these two product is also that this projection onto the component as each terms. Okay. Okay, so we prepared some consideration. First, the bosonic product. We rewrite the bosonic product by some component cyclic Ramon cyclic Ramon number by cyclic Ramon number. The bosonic product with this cyclic Ramon number 2r has two components. The Nebuchadnezzar component has this picture number, and the Ramon component has this picture number. So, of course, this bosonic product has no picture number. There are big picture number deficit. So the picture number deficit of the bosonic product is n minus r for the Nebuchadnezzar component and n minus r plus 1 for the Ramon component. So we defined some generative function counting this picture number deficit by this form. The picture number deficit is counting by this variable s, and which reduces to the bosonic L infinity algebra at s equal to 1. Then the L0 is nilpotent and satisfy the bosonic L infinity algebra. And by this generating function, this LBS satisfies these conditions that decompose it to the definition picture number deficit two component by picture number deficit, and then that this bosonic component. This means that the bosonic product is in the small Hilbert space, and then this is that extension of the L infinity algebra. Okay, this is the preparation, first preparation. On the other hand, if we introduce a generating function of the string product B, bit B, by introducing another variable T, counting the picture number. And so the L infinity relation satisfied by the D minus C is equivalent to these two equations. The B does not simply commute with eta, but there are second term. There is second term. We further extend B to those with arbitrary picture number deficit and define the generic function of that parallel to the bosonic string product. So now we have that two argument generating function PST. The S is counting the picture number deficit, and P is counting the picture number. The relation 2 is this relation satisfied by this D minus C is now extended to this relation. And we summarize that from this generating function, we obtain that simple generating function of the desired string products which we want. And we also, from this generating function, that we obtain that desired string product by setting the t equal to 1. And the other component, this function of S, generating function of the picture number deficit, is obtained by setting the t equal to 0. Then that the picture number becomes 0. Then, if we suppose that introduce the differential equation, if we introduce another co-derivation, degree even co-derivation, such as the generalization of the so-called gauge product, is by this form, and postulate the differential equation, this differential equation, then we can show that the left-hand side of these equations satisfy this differential equation. This is just a homogeneous equation. The derivative of t, derivative with respect to t, is just again proportional to I or j. Therefore, if I equals j equals 0 at the initial time t is equal to 0, then I equals j equals 0 for arbitrary time t. And however, the equation of this initial equation, the same form as a bosonic string product, this form. So it is satisfied by simply setting that this picture number 0 part is equal to the bosonic string product. Then, and then we differential equation can be written. Okay. And then the initial condition, we have this initial condition. If we set this condition, initial condition, then that by solving this differential equation, we can obtain all the arbitrary B string product at arbitrary time. Okay. So first we rewrite the differential equation as by this expanding by t, and the differential. If we expand, we can expand the string product by t, then the differential equation can be written in this form. And this we can show that this can be solved iteratively. by starting from that initial condition defined by the bosonic string product. Okay, I should skip that this consistency. Yeah, for example, that for n equals 0 case, n equals 0 means that the first order of the picture number. We set picture number 0 part of the string product is already set equal to bosonic product. Then the picture number 1 part of the equation has this form. This second equation is easily solved by this form, by inserting the Gucci zero mode to the symmetrically insert the Gucci zero mode to the bosonic product. And we denote this symmetric insertion by this Gucci circle product. Then, since lambda 1 is given, then this equation defines the first component of the string product. And so on and so forth. Yeah, similarly, arbitrary n b of the arbitrary picture number component can be determined recursively by this recursion relation. Okay, so we have constructed the string product. Okay. Yes, that depends on that how we first solve this equation. We solve this by as to be lambda 1 is cyclic, then the cyclicity is automatic. Yes. Yeah. All the insertion, Gucci insertion must be cyclic. Then that B is cyclic. Yeah. Yes. I think it is obvious. But cyclic with respect to the simple symplectic form without any insertion, picture number operator insertion. That is come from the cyclicity of the bosonic product and the, how to insert the Gucci zero mode. If both of that are cyclic, then the B is also cyclic with respect to the omega L. Okay, so we can we have succeeded to construct a B, that big B with the desired property. We construct a complete heterotic string field theory based on the homotopy algebraic formulation. Okay, next, we can also consider the Bessel-Witten-like formulation, the heterotic string based on the Bessel-Witten-like formulation. The gauge-invariant action in the Bessel-Witten-like formulation can also be obtained by the so-called field definition code. The meaning of the field definition is explained soon. Yeah, first we note that if we project these string product or gauge product onto the pure Nebuchadnezzar sector, the B and the lambda differential equation, this our new differential equation using that commutator 1, commutator 2, like new operation we introduce, reduced to the EKS differential equation. Differential equation introduced by Munich group. And thus, by construction, the component projected on to the pure Nebuchadnezzar sector is reduced to the just those of the EKS. So our action here constructed here is just the action constructed by Munich group EKS in the pure Nebuchadnezzar sector. Okay, this implies that L-infinity algebra restricted to the pure Nebuchadnezzar sector. This can be written in the form of the similarity transformation of this form. That is shown by EKS or maybe Okawa-san, Okawa Takezaki. And here that the G is a co-homomorphism defined by this gauge product by this form, by this expression. Then the big L used in the homotopy algebraic formulation is transformed by the inverse of this similarity transformation as this L tilde, this form. Here the B tilde is defined by this B minus purely Nebuchadnezzar sector component transformed by G. And we can, they show that this G hat preserves the cyclicity, then that this B tilde is also cyclic with respect to omega L. Okay, by this transformation, the small Hilbert space condition, that is a string field that it must be annihilated by eta, is mapped to this expression. Here that this eta is defined by the similarity transformation of the eta. That is a kind of nonlinear extension of the eta. That is introduced by Goto-san and Matsunaga-san first. The Nebuchadnezzar component, this Nebuchadnezzar component has the same form as that Moray-Cartan equation for the pure gauge string field G eta that is introduced by Goto and Matsunaga in the Besmino-Itten formulation. This form. Such a pure string field they called G eta. This suggests that this identification, the Ramon component is just equal to the Ramon component, and the Nebuchadnezzar component is mapped to the G eta B. Here that phi ns and phi r is the string components of the string field in the homotopy algebraic formulation, and B and psi is the string field in the Besmino-Itten-like formulation. Then, if you identify the associated field, so-called associated field B, DB, D is equal has two cases, D equals to T and D equal to delta. By this equation, here the big bold face CD is one co-derivation derived from this one string operation. Then, if we identify this quantity to the associated field, then that the associated field satisfies, we can show that this associated field is satisfied, associated field satisfies these characteristic equation, which is this equation characterizing that associated field that is followed from the identification, this identification. Then, the follow from the Okawa-san paper for the open superstring, the action in homotopy algebraic formulation we first rewritten that homotopy action in the homotopy algebraic formulation in the Bessemer-Witten-like form by introducing the one-parameter extension of the Nebuchadnezzar's component. And using the cyclicity property, we find that the homotopy algebraic action can be written in this form first. And using the identification, here, using this identification, we can further rewrite this homotopy algebraic action in the homotopy algebraic formulation to the Bessemer-Witten-like form. And further, we show that this identity satisfied by odd co-derivation L1, L2, using this relation, we finally, sorry. The final form of the Bessemer-Witten action is this. This is just a simple, already obtained Bessemer-Witten-like action in the pure Nebuchadnezzar sector. And this is a Ramon kinetic term. This is the interaction between the Nebuchadnezzar component and the Ramon component. Okay. So, yes. Yes. Then we can also map the gauge transformation. Since this pure string field, pure gauge string field in the Bessemer-Witten formulation, the arbitrary variation with this pure gauge string field is defined by as this form. Then this identification is not one-to-one, because this pure gauge string field is invariant under this transformation. The eta square is equal to 0, then that this is inert under this gauge transformation. So this is the redundancy of the map from the homotopy algebraic formulation and the Bessemer-Witten-like formulation. In addition, of course, that we have gauge transformation in the homotopy algebraic formulation. It can be mapped to the Bessemer-Witten-like formulation. The result is this form. Here, that gauge parameter in the two formulation is given by this. Again, that the Ramon component is just identified. That the Nebuchadnezzar's component of the gauge parameter has this non-trivial map. This is just a mapping from the homotopy algebraic formulation to the Bessemer-Witten-like formulation. But if we obtain that, once obtain that the Bessemer-Witten-like action and the gauge transformation, we can independently show the gauge invariance without referring the homotopy algebraic formulation. Okay, I should summarize my talk. So we have constructed complete action of the gauge and gauge transformation for the heterotic string field theory in both homotopy algebraic formulation and also the Bessemer-Witten-like formulation. So the first chart I should mention in the introduction is completely filled for the heterotic string case. And we also, I could not mention today, we have also confirmed that the 3-level 4-point amplitude are correctly reproduced in this in the homotopy algebraic formulation of heterotic string field theory in the homotopy algebraic formulation. And I should also mention that the extension to the type 2 superstring field theory is rather straightforward, and the work in progress now. And of course, the construction of finally, I should mention that the construction of complete action is not the end of the story, but just the beginning. I believe that the string field theory provides a solid foundation to study various interesting properties of the heterotic string. Okay, thank you very much. Sorry?
You introduce an extended infinity algebra.
No. Just a infinity algebra, but space acting that the infinity algebra is extended.
But the algebra is always the same.
Algebra is same. The infinity algebra considered here is acting on the direct sum of the Nebuchadnezzar-Hilbert space and Ramon-Hilbert space. The infinity algebra already constructed is just acting on the Nebuchadnezzar sector.
Yeah, but the axioms are always the same.
Yes. Yes.
Oh, if you transform your infinity structure with this field redefinition that we
Mm-hmm.
constructed in Munich many years ago,
Mm-hmm.
you get some kind of infinity structure that has a nice final graph interpretation.
Yeah.
Yes?
Yes.
What are the final graphs?
Okay, so again?
So if you take the infinity structure
Yes.
that you derive,
Yeah.
and you transform it with the field redefinition
Mm-hmm.
that we constructed many years ago in Munich.
Yeah.
Okay. The question is whether you get an L-infinity structure that has a nice Feynman graph interpretation using in terms of a complicated connecting.
What you mentioned about by your construction? Our construction is reduced to your construction in the pure Nebuchadnezzar sector.
Yes.
Yeah.
Right. So if you okay, maybe we
Sorry. Mm-hmm.
You completed the formulation, but my understanding that you first constructed the new construction, extended the sector.
Yeah.
You define the field definition
Mm-hmm.
at the base of the unit.
Yes.
But previously you were working with field control on the
Uh-huh.
condition of the base.
Yeah, partial construction, yes.
So that is the so you
Relation of them too.
so previously it was not complete, but now you
Mm.
that it's
Yeah.
how did you
The correspondence, I think that correspondence is quite complicated, but that should be related to by field redetermination.
So your previous one is different from the previous one.
Different, yes. Yeah. At the work by Goto-san, we only used the nonlinear extension of the eta L infinity based on the eta. The string product is all the string product is in the part of the L infinity in the eta we call that dual L infinity. But here that the product is just a string product in the conventional L infinity. But but a little bit we use the eta product is only appeared in the pure gauge string. That's in some sense that the hybrid. Yeah. Yes.
So you say that
forward. The similar construction by Munich group, a so-called asymmetric construction. First construct the left moving part and the right moving part. But of course, that we have some problem to construct the kinetic term of the Ramon-Ramon sector. Yeah. So we have two choices to impose the constraint and have some non-local kinetic term, or introduce additional auxiliary type field proposed by similar by Sen. Yeah. Yes. Yeah. Yes. But yeah, but I think that non-local kinetic term is apparently it is not good, but I think that I don't know. So for interaction, kinetic term, yes.
yeah, I think if you use non-local kinetic term, then probably you can write down a kinetic term for it.
Yes.
Right? It's only the local action is difficult.
Thank you very much.